It's time for Pure Performance.
Get your stopwatches ready. It's time for Pure Performance with Andy Grabner and Brian Wilson. Hello, everybody, and welcome to another episode of Pure Performance. My name is Brian Wilson, and as always, I have with me my amazing co-host, Andy Grabner. How are you doing, Andy?
Good. That's an exciting day today. Do you know why?
No.
No, because obviously you're not following the Euro Cup, because at the time of the recording, we're only 1 hour away of the most important match in Austrian football, or as you call it, your soccer history, because we need to at least score 1 point against Holland. If we do that, we make it to the next round, and that's going to be exciting.
Yeah, I thought football season was over, but that was back in February. No, I'm kidding. You know, it was really interesting, Andy. I was I don't know why, but for some reason yesterday I decided I'm going to turn on the FM radio. You know, I don't know who listens to FM radio anymore. But I was turning down around the dial, and I found a brand new station that was playing all of some amazing songs. I don't know if you ever heard of it. It was WASM. It was a pretty cool radio station, I gotta say. Have you ever heard of that one before?
No, but WASM, that sounds very closely familiar to something else, but not on radio. I don't know.
Oh, no. It was, anyway, there was a long distance dedication sent out to you. Yeah. It was Rock Me Amadeus, somebody sent out for you. And anyway, it was a cool station, so I wanted to share it with you. And yeah, that's the only story I got today.
Yeah, it's an interesting odd intro, but yeah, maybe now time actually to Wasm, or WASM, as you call it, Wasm, WebAssembly, the topic of today. And neither Brian and I have any clue about it. Well, a little bit maybe, but not much. No. Not a radio station, but to actually learn more about it, we invited Matt Butcher. He's not a butcher, but he has an awesome last name. But he's going to help us, hopefully, learning more about Wasm. Matt, thank you so much to join the show. Sorry for all the initial trying to be funny episode.
Yeah, thanks for having me. And I'm pretty sure that the first song you heard, Brian, on that new station is "Everything is Awesome, Everything is Cool." And
hey, there you go. That's a great one, yes.
And now that I have a song, the show's already over, right?
Yes.
Yeah, we lost 2 of our 3 listeners already. Thank you. Hey, Matt, in all seriousness, I'm looking at your LinkedIn profile, and I always thought I'm contributing quite a bit to open source. But if I read yours, I'm a founding member of dozens of open source projects, including Helm, CNAP, Crustlet, Brigade, Open Application Model, Glide, and the list goes on and on. You have published several books. What have you not done?
Well, up until just recently, it was sing on a show. But now that I've not knocked that one off, I think we're... Yeah, perfect. I got started in open source. Like I'm one of those really fortunate individuals that even my very first job in high school in the 90s, I was working on open source projects. And so I have had a long time to do dozens of projects. So I might have underdone it. But yeah, I've been involved in a whole bunch of communities over time, including, the PHP community and the Drupal world, OpenStack, and then the Docker and container and Kubernetes ecosystem. And these days it's the WebAssembly ecosystem.
Mm-hmm. What is WebAssembly for those that have never heard WebAssembly? Can you quickly highlight why this is a technology? What's the problem that this technology tries to solve? Why should people be aware of it if they're not yet aware of it?
So WebAssembly is a technology that, like many other really great technologies, sort of outgrew its original purpose. So back in 2015, a group of developers from Mozilla sort of rallied a bunch of browser developers from all the major browser companies. So some people on the Safari team, some people on the Chrome team, some people on what at the time was the IE Edge team, to all work together to solve a problem that we've taken several runs at before, but to try it in a slightly nuanced way. So, like I said, I got started in the 90s when dinosaurs roamed the earth and, Netscape Communicator was the cool browser and all of that. And this there were a couple of languages that looked like they were going to be the browser language of choice at the time. And the first one was Java, right? Java was supposed to run in applets in the browser, but they needed sort of a glue layer to help Java, bind itself to the browser objects and things like that. And so the Brendan Eich at Netscape created what was originally called LiveScript and later was renamed JavaScript. And those were the two big languages. Then for a while there was VBScript, right? They were all kind of contending for browser dominance, right? And Java had this cool technique that the scripting languages did not have. And that was that you could write the code on anything from a Solaris workstation to a Windows 95 workstation or all the different things that were fancy at the time. But you could compile them to a single bytecode format, the Java bytecode format, and run it in any of the different browsers that were out there at the time, all two of them. It was the first real attempt to run a bytecode language inside the browser. And as we all know, it did not succeed. Right. Yeah. Part of that was because it was a commercial offering. Part of that is because it was really slow. Part of that is because Java itself was an immature language, but it did not deter people from trying different ways of doing this. Right. So Silverlight came along, Flash came along, a variety of other answers came along, but each one sort of stumbled and fell, often based on the fact that they were proprietary, right? Only one browser supported it, or the language itself wasn't open source or whatever. So in 2015, as this consortium of developers from all the browser makers get together, they said, we want to take another run at this, but we want to be a lot more modest in the way we approach the problem. Instead of trying to build a sort of soup to nuts solution that handles everything from a language and a bytecode format all the way up through like the windowing toolkits and all the things that these other animations and all these top level things that Adobe and Microsoft had tried in the past, let's just solve one problem. Let's create a bytecode format that can be cross-platform and cross-architecture and run well in the browser, like really fast in the browser. And if we can just solve that, we'll let other languages, existing languages, compile to that format, and we'll let other people solve the higher order problems. And so that was really where WebAssembly was born. And if you sort of look at the features that you would need to do that well, you see maybe 4 different things. The first one is you want a really good security sandbox. You want to protect the browser from opaque binaries that are going to get downloaded off the internet and executed on your machine. You actually want to protect your JavaScript sandbox even, so that something gnarly that happens inside the WebAssembly runtime doesn't, slow down your JavaScript and slow down the browser and everything. So it needs to have a really good security sandbox. It needs to be really, really fast to execute, because we all know we are not patient when it comes to websites loading. It needs to be cross-platform and cross-architecture, because as we know from the browser world, it needs to run on everything from like Raspberry Pi to, supercluster to the refrigerator, anything that you can shove a browser into. And it needs to have smaller binary sizes, because, you're moving these things around the network. And so those were some of the big design goals for WebAssembly. And, as a technology, it took off pretty well. You see it used in Office, the online version of Office. You see it used in Figma. You see it used in a variety of places where either old libraries, the Office case, an old library that was written in C is compiled to WebAssembly and dropped into Excel, so that nobody has to rewrite that old gnarly C code in JavaScript. Or you see cases like Figma, where in order to get high performance vector graphics, they wrote their core libraries in C++, compiled them to WebAssembly and put them in the browser. So that's kind of the heritage of WebAssembly as a browser technology. But what excites me is that particular technology has had a lot of room to grow and has actually shown up in a variety of surprising places, including kind of the way that Fermyon uses it.
So that means today, help me, I'm here sitting in front of my laptop, I'm running a Chrome browser. That means I have a Wasm runtime in my browser.
Yep. Yeah. Every major browser currently supports the WebAssembly 1.0 final version of the spec. WebAssembly, by the way, is standardized, and it's standardized by W3, the same standards body that does HTML and CSS. So it is considered a core web standard, thus, pretty uniform adoption across all of the web browsers.
Yeah. Where on which runtimes and which devices maybe would you love to see Wasm, where you thought it should be there already, but it might maybe not, maybe the adoption is not there, or somebody didn't port it over? What are people asking for?
Well, and this is where it gets interesting, because as a browser technology, it's kind of landed in all the major browsers, right? But as a runtime technology, there's no reason you couldn't take something like WebAssembly out of the browser and run it in different environments. In fact, that's what we do, right? We kind of pulled the WebAssembly runtime out of the browser and built a server side runtime, and on that side, then it's getting really interesting, and I'm excited to see this happen, right? It's getting really interesting to watch it show up in embedded devices and in gigantic server farms, right? We have been playing around with this Ampere 256 core ARM board and trying to get WebAssembly mega interpreter that runs across all 256 cores, right? But you also see it down to sort of small form factors of devices. So where we're seeing it now, and what's exciting, is some of the more exotic, like RTOS and small embedded operating systems that are starting to get support. But I'm looking forward to seeing that kind of come to fruition over the next few years. There are some good starts to that, but of course, as you know, there are a lot of embedded devices and a lot of different pieces of hardware and small operating systems that it needs to be ported to yet.
So then also I know these are all probably basic questions for you, but for the benefit of me and Brian and the listeners that have not yet had the time to look and dive into Wasm, then what type of applications are people building? Is it serverless applications? Because I hear a lot of Wasm talk around serverless, like you're building lightweight functions. Is this kind of like the a standard that would replace some of the more specific offers that the cloud vendors offer, like a Lambda, Azure Functions, Google Functions? Is this what people are trying to do? Like use it as a standard to build serverless apps, or what else are people doing with it?
Yeah, absolutely. I mean, we've kind of seen 4 distinct areas where WebAssembly is gaining traction. The browser we already talked about. We are starting to see embedded use cases for WebAssembly. BBC and Amazon and a few others, they're embedded streaming players that you're probably watching on your Roku or your Apple TV or whatever. Those use WebAssembly. They actually, you can write a very small shim that binds your hardware to your WebAssembly runtime to the application, and then you can run the same application code in a wide variety of devices. That's a great story for cases like that. We're seeing some of it used in plugin architectures and databases, but the one you pointed out is the one that I'm most excited about, and that's cloud. And to jump right in, to that one, as I told you, I got started in OpenStack, and OpenStack, when I was first beginning to work on it, OpenStack was entirely based on the virtual machine world, right? The containers were not really a thing at that point. And, so we had containers, networking, storage, virtual machines, networking, storage, and, what we saw happening then, and this is, rewind 10 years, 12 years from now, right? What we saw happening then was this sort of breakdown of the one-to-one relationship between a piece of hardware and an operating system, right? You went from installing one operating system on one piece of hardware to suddenly having one piece of hardware with potentially dozens or more virtual machines on it. And that was a really exciting time. But, you are talking about packaging an entire operating system up and running it in an environment. So some of the early projects I did, using virtual machines, we were writing an application that was 2 meg. We were packaging it up into a 6 gig Linux image and shipping it up to Amazon to run it for us. And it, at one point you're kind of going, this virtual machine thing is cool, but that's an awfully big image and an awful lot of data shuttling. It took us 3.5 hours to deploy our N-copy cluster of this app. That's an awful lot of space and time for a 2 meg app. So, the virtual machine world was definitely solving problems. Actually continues to be sort of like the battleship of the cloud world. But when containers came along, we had a second option, right? If you're working on long running processes, you can package them inside of a container instead of in a virtual machine. And instead of talking about gigs and gigs, you're talking about maybe hundreds of megabytes or even tens of megabytes of data And so suddenly this 2 meg app is only instead of being a 6 gig app when it's all packaged up as a virtual machine, was only, I think at that time it was probably about 40 or 50 meg because we were using the Debian Slim version. Yeah. So we had, two solutions there. We had the virtual machine solution, we had the container solution. And for long running processes, we were starting to see databases and the kind of burly things that need to run for a long period of time sort of land on virtual machines. And then for a while, it was the microservices that were landing on containers. And things have matured and lines have blurred over time, but that's the way it was sort of when Kubernetes was new. Then Amazon came up with this interesting idea that was, we got all this excess compute. Wouldn't it be cool if we could schedule this compute to be used for only little time slices instead of, long-running virtual machines? And they built Lambda basically in order to consume the excess compute. And the original idea was like, this is for utility computing. If you need to respond to an event here and shove something over there and time doesn't matter and length of execution doesn't really matter, Lambda was a great solution. And of course, Lambda really took off. I think a couple of years ago when I was at reInvent, they said they execute 1 trillion with a T Lambda requests per month. And so that's 1 trillion runtimes that got started, handled a request, and shut down in 1 month. Far, far beyond, I think, what the original scale was they intended. And part of this would be because the method of writing serverless functions is just so easy, right? Instead of writing a long-running server that's hundreds or thousands or hundreds of thousands of lines of code, you're just writing an event handler, right? And it takes a request, it does something, returns a response, and shuts down. And
eventually, right? I mean, that's exactly what in the end, this big thing that you just talked about is just handling individual events. They are coming in as requests. So in the end, it's a perfect fit for Lambda, right? Handling individual requests.
Yeah, exactly. Yeah. And so, I was by this point in my career, right, I was at Microsoft. And so I'd gone from, HP working on OpenStack on into Microsoft working on Kubernetes and containers. And, we were looking at the way that Azure functions, Azure's competitor to Lambda was running and going, wow, this is kind of wasteful, actually, because you're spinning up an entire virtual machine. In fact, you were spinning up thousands of virtual machines, queuing them up so that when a request came in for an Azure function, a virtual machine would get slated to handle that. The code would get dropped on that virtual machine, executed, the request would be handled, and then the entire virtual machine is torn down and a new one is spun up and pushed on the end of the queue. And the reason you do this is because you need this high degree of security. Yeah. And frankly, they didn't have a technology at the time that could handle it. I learned that actually that particular design pattern was exactly the way Lambda was implemented too. So you have these huge queues of virtual machines. And because so much work has to be done real time, right, at last possible instant, the cold start times for serverless functions were in the 200, 500, 700, 900 millisecond range, right? Any of y'all who are browser developers hear these numbers and go, oh, that's cringeworthy, right? Because Google starts dinging you on your search results at around 100 milliseconds. So if you're not returning data in the first 100 milliseconds, then it's starting to harm your SEO. When you're not even cold starting for 200 to 500 milliseconds, you're never going to be able to build a really high performance website. Likewise, you're not able to build high performance, job handlers, scheduled workloads, things like that. You're always taking a delay at the beginning. So here we are at Microsoft looking at this problem and going and trying every which way to figure out how to solve it. We were trying it with containers. We played around with unikernels. We were playing around with all kinds of things. And we went, maybe the way we're thinking about this is all wrong. Right, we're kind of entrenched in this heritage of virtual machines and containers being the two classes of cloud compute, and everything else in cloud compute being built on those two abstractions. What if there's a third kind of cloud compute that had all the properties of a good cloud runtime, right? Security, portability, all that kind of stuff. But in addition to that, was just highly optimized for lightweight workloads that would run in this kind of serverless paradigm. And that's actually what got us looking at WebAssembly. So, we really were like looking everywhere and went and said, oh, this thing that was built for the browser, this actually pairs perfectly. This checks off all the check boxes for what we're trying to accomplish on the server. And so we started building, a cloud side runtime for serverless applications. And that's where Fermion was born, right? We saw a need, we saw a big challenge, and we found a potential solution for that, and have just been spending our last 3 years kind of developing both the developer tools for that and the cloud runtime for that.
So that means huge resource gains and efficiency gains on the operating side of all this, right? Because as you said, it's crazy to think about that for every request you have to spin up and then tear down a full VM. And it's just like a lot. And I just like the example that you brought earlier. For a couple of 100 lines of code, you need to package everything up into a big, either multi-gigabyte image or even in a container, and that's just a complete waste of time. And waste of resources. So that means, what are there any limitations? Like if I think about building this, are there any limitations I have to be aware of when I want to build something? So is there anything where you say WebAssembly is not the right thing? You still need to go with a container or with a whatever other serverless framework?
Yeah, and I'll give you two. There are two kind of big ones. The small one and then the double extra large one. So the small one is, as WebAssembly does not handle multi-threading, and there are a few other features like that WebAssembly does not provide yet. It's coming. It's in the works with specifications and things like that. There's actually the work that goes into building a multi-threaded runtime for lots and lots of programming languages is intense. And in particular, when you have to share threads across instances of a WebAssembly runtime. But the work is all coming along very well. There's an asynchronous runtime implementation that's coming out soon. But there are a couple of things like that, right? Networking has been a little bit slower. Low-level networking, high-level networking like HTTP, piece of cake. Low-level networking, much, much harder. And so there's some features like that are still working their way through specifications. And the workaround so far has been that the runtimes will provide sort of a native, not WebAssembly implementation of some of these things and expose those to developers so that they can keep working. But that does mean that, some off-the-shelf libraries don't work, right, as expected. Any language that's heavily uses threading libraries underneath the hood, you end up doing either some library rewriting or some picking and choosing. So that's one. WebAssembly's biggest liability from day one has always been the rather audacious expectation by the original WebAssembly developers that if they build it, everybody else in all the different language communities will suddenly say, hey, we'll write a C to WebAssembly compiler. We'll write a Rust to WebAssembly compiler. We'll write a Python WebAssembly runtime. And so its biggest risk has always been that it wouldn't be able to handle the major programming languages, if not all the programming languages. And that one's big, right? Because again, just to be crystal clear on what the expectation here is, you write a specification that says, if you can compile it to this bytecode language, we can execute it. But you leave it to every language community to say, this is how we get from our Python source code to a WebAssembly binder, from our .NET assembly to WebAssembly. And the remarkable thing is that right now we seem to have kind of hit the kind of critical mass, and we are seeing language after language starting to add support. So C and Rust were very, very early. Rust, I think, is sort of like what Go was to the Kubernetes ecosystem, where Docker and Kubernetes were written in Go, so seemingly everything was written in Go. Rust is kind of like that for the WebAssembly ecosystem. The kind of core reference implementations were written in Rust, and consequently, you see a lot of Rust. You see Rust is kind of the dominant language in the ecosystem. So you saw a couple go early, but then kind of like dominoes, things started to fall, and you started to see, Python and then Ruby and JavaScript and some of the interpreted languages build it so that their interpreter could compile into WebAssembly, and then go from there even farther beyond that. .NET 9 has support for WebAssembly in it right now, and it's due out, I believe, November of this year. But we've already been working with the .NET team piloting their stuff inside of Spin, and it's really cool. So there you're seeing a bytecode language. So the first wave languages, right, C and Rust, were basically compile it to native kinds of languages. languages, and they moved fairly quickly. Then you saw some interpreted languages go, and now you're seeing some bytecode languages go. And that pretty much runs the gamut of the different language types. And then we're seeing language after language get support. So Zig had it fairly early. Swift now has it. And I think the kind of the big laggard in this world is Java, right? The Java community has, somewhat, I wouldn't say stagnated, but they're in a rut, right? They have a way of doing things, and they have not been as flexible or as quick to adapt as technology has changed, right? It was hard to put Java in containers. Now it's hard to get Java in WebAssembly. So, hopefully that one will move. And I think Java is the last big language. Going back to your question, you kind of have two things going on here. On the one side, you got this audacious requirement that lots of languages will move. And then on the other side, you've got sort of like core operating system constructs like threads or like low-level networking sockets that were not part of the original WebAssembly specification, which was designed to run in the browser, but are part of the current draft specifications that are on their way through standards bodies. And in the interim, until those land, it makes a certain class of application hard to write. And that, by the way, is how we ended up at serverless, right? We started with serverless, right? We were looking for a runtime that could do serverless really well. And one of the things we were totally willing to give up in a serverless environment was threading. Because if your thing is going to handle a single event to completion and then shut itself down, the cases where you need threads tend to be fairly rare, right? You're really take an event, handle it, send a response. I mean, I was a PHP developer for many, many years. We didn't have threads. We were happy with it, We just wrote web pages. And I think WebAssembly is kind of in that, you can sort of mentally categorize it in that family of language or that family of feature sets right now, right? Great for single-threaded things, nearly impossible to do with multi-threaded things for now. And probably it'll be another year or so before you see the really great threading support in it.
Yeah. Hey, from an observability perspective, because that's, the kind of area where Brian and I obviously spend most of our time, is there anything built into the runtime, into the specs of the runtime to make it observable? Because I think that's obviously critical. And also thinking about how lightweight it is, we would hope then and assume that also observability is very lightweight and following standards like, I don't know, is it exposing OpenTelemetry? What's happening on the observability side?
Yeah, so Fermyon is building a developer tool called Spin. And Spin is kind of the tool to help a developer go from, blinking cursor to deployed application, right? All those steps along that process. And then there's a Spin runtime that's the serverless WebAssembly runtime. And so really in both cases, as we built this, we've asked that same question. How do we make what's happening in the WebAssembly visible to the developers on one side and visible to the operations team on the other? So I'm going to start at the high level and go down because what's there today is table stakes, right? OTels, or sort of open telemetry support, standard observability of the sandbox environment that you're running in. All of that is fairly easy to add, right away. This is one of the nice things about the way WebAssembly works. You have a single runtime, unlike Docker, where underneath the hood, Docker's sort of an assemblage of different pieces and parts of core Linux operating system. And it's just sort of orchestrates the standing up of C groups and just sharing the kernel and all of those kinds of things. WebAssembly, all the code is running inside of a single runtime. So you have one runtime that you can instrument and say, spit out telemetry about how much memory is being used, how much CPU is being used, that kind of thing. But there's, if we are to look a level deeper, right, if we're starting to go down into what's happening, in the virtual machine world, the runtime was handling the lowest level of instructions, right? Machine level instructions. And they're basically opaque to the runtime as to what's actually happening. You'd have to reconstruct so much context to see what's actually executing in a virtual machine that, frankly, as far as I know, nobody but probably government level hackers have ever even tried doing these kinds of things, right? You just assume you'll have to instrument inside the virtual machine. Containers actually fairly similar, right? The what's running inside is relatively opaque to the runtime outside. You might know process IDs, you might know some of the memory details, but that's about it. If you want to see what's happening inside the application, you go to the developer and say, hey, can you instrument your application, right? Can you add some stuff in here that emits events? WebAssembly is the opposite opposite end of this spectrum, right? You're getting the language as byte codes, and you're getting it in the form of instructions, the instructions that are happening inside of the program. So you can actually observe a WebAssembly and say, this function was just called. Now this function is just called. Okay, this function seems to have been called about 60,000 times in a row. You might have a recursion problem, right? Or something like that. And so you can actually instrument externally the WebAssembly binary. Now it comes at a cost, of course. Anytime you're observing anything, you're imposing a performance penalty. But where we think we're going with WebAssembly would be sort of like a utopian world for operators, right? Where something's going wrong and you go to your dashboard and say, okay, turn on deep tracing on this particular instance of this application, and it starts spitting that out, and you bundle it up and send it to the developers and say, what's going on in production, right? And give them the tracing output without, I came from the sort of ran a major website, and we used New Relic to instrument our code. And we would end up in those cases where something would go wrong in production, and the ops team would call us and say, hey, something's wrong on this particular part of the site. And we'd go in and dump New Relic, function calls into all the way through the stack, and then ship a new binary to them, and they would run it. And if they could reproduce the problem, then we'd get the trace information back out. We couldn't log into production. It was against the rules. They couldn't do anything to turn on instrumenting on their own. We see WebAssembly as maybe getting us past that, right? Where the operations team could say, something's going badly now. Let's see what it is. Turn on the switch, record some stuff, turn off the switch, ship it to the developers, and start to reconstruct, and let them start to reconstruct what's going on. That I think will be a leap forward as far as how we can do observability in the future. So today, very much WebAssembly is in the table stakes world of being able to do all the kinds of things that we've worked on in the container and in the cloud native ecosystem as a whole, right? But I think tomorrow it may be even more promising.
Just one clarifying question. Thank you so much for all the insights. But just want to clarify and if I understand this correctly. Are you suggesting when we want to instrument code that we are actually instrumenting the bytecode and basically make the bytecode then emit telemetry data, or do you see this more in the responsibility of the actual runtime and therefore pushing it to the runtime developers on the individual operating systems to emit the code? I wasn't clear on that.
I think it will end up being in the WebAssembly runtime that you would have to say, allow the user to give me a function, and then I will be able to emit the tracing for that particular function. All right, and I mean that's the way we have approached it. And there's sort of like, there's sort of like some standard runtimes out there that work on a variety of operating systems. We run the actual WebAssembly interpreter, or the actual WebAssembly runtime that we use is called Wasm time, and is created. It's sort of a reference implementation of the WebAssembly plus WASI we haven't talked about WASI much. We should talk about that in a little bit, but it's a reference implementation. And so we figure if instrumentation makes its way into that level of software, then you'll start to see it really kind of crop up everywhere. But you should be able to do this, right, without recompiling or redeploying or anything, because really all you're saying is, hey, I know there's a function in there called exec foo. Tell me what exec foo is doing right now. Oh, that's not it. What about exec bar? Oh, there we go. That kind of thing.
Yeah, and that also means the bytecode standard that still has the concept of functions and function names. They're all preserved, because otherwise it will be tough to say, hey, which function was actually, what was it called? Because you want to, in the end, link it also back to your source code. I mean, I remember, and I know in some of the other bytecode languages, when the compilers are basically transforming your code into bytecode, then you have mapping files, so you can always then map it back to the original source code line, so you can actually provide good debugging tools or developing tools and so on.
And I imagine in some ways it'll have to run analogous to that. But the interesting thing is most of that transformation happens at startup time, not at compile time. You compile to a WebAssembly binary, and you can still, to my knowledge, you can still see within reason the names of any exported function, any public function, right? And there's, so actually you get us into an interesting realm, which is to this point, we've talked about WebAssembly as being, in some ways running parallel to, say, Java or .NET or these other kind of bytecode languages. And yes, it has some pros there, right? That make it a uniquely good fit for what Fermyon wants to do. Fast startup time, good security sandbox. Those are really important for what we want to do. But what makes WebAssembly interesting is that there's a feature in there that no other language environment really has. And this is where we start talking a little bit about WASI, the WebAssembly system interface, but more specifically talk about this thing called the component model. So let's, if we were to back up to where are we, right? Well, we've got WebAssembly binaries. WebAssembly binaries run inside of sandboxes. The original design for a WebAssembly binary was, hey, I'm going to compile this old crufty C library and drop it in the browser, and then JavaScript can call in and out of this. Or in Figma's case, I'm going to write this fancy new C++ high performance vector library so I can have my JavaScript call into it and do all the number crunching and send me back the numbers I need faster than I'd be able to do it, right? So it was a language designed to make libraries accessible. Not just top-level main functions, but libraries. It's also designed to be language neutral, right? So I can run Rust, I can run C, I can run Python. So it should, in theory, be possible to say, hey, I wrote this in language A and that in language B. I got a Python library, I got a Rust library, and I'm writing some Go code, and I want to compile all of that together into one WebAssembly application, or assemble all of that together into one WebAssembly application. And that's what the component model allows you to do. Basically, it's a way of saying, hey, this library exports these functions, and this application needs to import these functions. And then the WebAssembly interpreter says, okay, so I'll start up, one of your main things and one of your library things, and I'll run them both side by side and let them communicate with each other. And so there's a case with two components, but there's no reason you couldn't have hundreds or even thousands of components all running. Now, the way that this actually runs is where things start to get interesting, because you've got two binaries. Each binary is running in its own sandboxed version of the runtime, right? So, binary A, my high performance vector library, and binary B, my serverless function, they can see the functions that are imported and exported, but they can't see each other's memory. So those of you who work in compiled languages or who have been following some of the recent big security vulnerabilities know that you compile all of these into one big binary object, and there's nothing stopping a misbehaving library like, say, a compression library, say, from attacking using functions in another libraries that another library controls the memory for, whatever, like, say, OpenSSH. And so you can end up with some very dastardly dependency injection things. Well, in the WebAssembly world with components, that simply can't happen. It's just the public interfaces that they're allowed to access. The memory is completely separate unless they decide mutually to share the memory. And so you start to see a possibility for building a new kind of application where you, instead of us constantly rewriting the exact same functionality in every single stupid language under the sun, you can say, I got a Rust YAML parser, I got a JavaScript, date parser. I'm going to import both of those into my Python code, and all is good.
Yeah.
But then the security part means we can also start to say things like, oh, by the way, that Rust YAML parser, I don't want it to have access to the network. So disallow it from using any network requests. And that JavaScript date parser, I don't want it to access the file system, the network, or even the system clock, which would be weird for a date parser, I suppose. And you can kind of turn on and off security for each of these modules. So you start to see a glimpse of what the world could look like if WebAssembly and the component model began to be sort of broadly adopted. And that, I think, is what's really exciting. That's where we see, WebAssembly going from a convenient replacement for serverless runtimes into a new kind of ecosystem that's opening brand new opportunities for fun and new ways of writing code that is hopefully far less wasteful of our time and resources, and far more secure and observable, right? Because anytime those function calls are going across modules, you can literally say, hey, tell me anytime this library gets accessed, because I want to know. Or, we've got this internal running what if kind of thing where we're going, what if, you discover that OpenSSL had a vulnerability in the, calculate foo function. So you wrote another component that said, hey, I'm going to wrap the OpenSSL thing, and anytime somebody calls calculate foo, I'm going to sanitize that request. Any other time, I'm just going to pass everything directly in and out. So you start to see emerging this new way that we might be able to handle, security, observability, software development, and it's exciting. I think that's what really gets me going on WebAssembly's potential.
You can obviously feel it that you are excited about it. And for me, thank you, because when you started talking about this, I thought, why not compile all of these different languages into one binary? Because in the end, it's all in everything gets compiled into the same intermediate language. But I think the benefit, what I now understand, is that you can run all of these individual components in isolation as a component. And therefore, also to your SSL example, if you have a vulnerability, you can just replace this particular piece, and you don't need to recompile all of the other apps and updating it with a new version of the library that doesn't have the vulnerability. So you really, basically, in the end, it's all microservices as well as functions. Everything is kind of isolated and encapsulated. I really also like the fact that you can give it individual privileges, so you can basically say which component runs in which particular security context, so you can actually secure it and give it just a least privileged approach, right? You just basically say, what does this particular capability need? It doesn't need access to the network, so we don't give it access to the network. So it's really interesting. I could also then obviously see the more flexibility we provide here, the more challenging it will become to actually understand what is really going on as things are executing, because you have component A calling B, C, D, and then you have everything runs in a different security context. That's why observability, again, needs to play a vital role in all this.
Yeah. And I think, I'll give you an anecdote, here, and then, because everything you said is dead on, right? That's why it's so exciting. I was at Microsoft when a low-level library, open source library, had a major vulnerability, and how did the operations team have to handle that? Well, they had to say, all right, we got, 1,400 or so applications that were impacted by this, all of which are containerized. We can't actually do anything. We have to send it back to all the developer teams who built all these applications and say, hey, y'all, stop everything you're working on, cancel all your meetings, patch these right away, re-upload all of these, and we'll redeploy them. And that's disempowering to the operations team, because they're stuck not being able to do anything. And it's really frustrating for the engineering teams, who all had their work interrupted that day in order to do a high priority patch. And that kind of experience is one of those where it comes to the forefront that we have built technologies that introduce human friction into a human process of software developers packaging their applications, shipping them to platform engineers running those applications, encountering issues, having to go back to the software engineers, ask for things to be instrumented, right? We've got this back and forth that we know is the source of so much tension. Right. And people get grouchy when they have their work interrupted, and people get grouchy when something's going wrong in production and they can't do anything until the developers, go fix the problem. The component model might help us toward a solution there, if we could say, as you just said a moment ago, right? Oh, SSL bug. We will redeploy the SSL component with a fix or with a, web application firewall style wrapper on it. And that's a thing that the operations team often can do, or can do with the help of only one developer team instead of all the developer teams. And if your application is just assembling components, then, all it takes is redeploying this component into all the applications. And conceivably, we can envision a world in which the Microsoft scenario of 1,400 services all becoming vulnerable on the same day, resulting in 1,400 teams having to stop their work to fix it, to being really more of an operation problem, where that same level of vulnerability would just involve a small number of people saying, okay, we got to patch this one, calculate foo function and recompile WebAssembly into recompile OpenSSL into WebAssembly, and then redeploy this thing out to everywhere. So it does have some exciting things. And as you point out, observability in this case is both the difficult part and the kind of fun part, because in a way now one debugger is not just going to be able to watch everything that happens start to finish, because you'll be calling in and out of different bytecodes. But on the flip side, the observability on the operations side may be just leaps and bounds farther than what we have now, because we can say, hey, this one module here, this one component seems to be the source of problems on applications A, B, and C. Something's wrong here, and be able to diagnose things that previously were completely opaque to us as platform engineers.
Yeah. Two final thoughts on my end, because I know we are kind of approaching the end of the recording hour here, but on this, I think we also need to be careful though, because if let's say we made the jump from one monolith to 100 microservices, we may make the jump from 100 microservices to 10,000 components if we really decide that everything becomes its own component, right? I mean, that's from scaling and from managing 100,000 small components. Like if you really go do it as granular as like a date function, a formatting function, then the question is, are we going too far? I think I guess that will be the interesting thing. Like how small do we need to go? How micro? So that's going to be interesting. Like how do you manage all of this? And then the second question, it sounds nice that obviously every component can then call another component. And it seems it's being very efficient, but still calling something that is outside of its scope means you need to cross scopes. That means there's always some type of overhead involved in making two components talk with each other that don't run in the same kind of space, right? So I guess I assume that I hope there's a good education going on how small should you go, and also what's the overhead, because there's always overhead in communicating, right?
Yeah. Yeah, and I mean, I think we're with the risk of talking to people like me is that, I'm looking out there going, I think we can do this. I think we can do this. I have no idea what the best practices are going to look like a couple of years from now, right? Because in some ways, we need to start building applications and learning which way is the right way and which way is the wrong way. And I do share your concern that if we tried to literally componentize at the library level every single thing, we could certainly end up in this case where I was looking at Node applications a while back, and to do an Express Node application with a database connector was 100,000 lines of code. But it's also something like 1,400 libraries or something like that. We don't want to run 1,400 WebAssembly components in order to do Hello World, do we? Probably not. So we're going to have to we're going to have to invent some architectural patterns as we go to say what is the right level of isolation or whatever it is that's the characteristic we care about at that time. Right size of API surface, I don't know. I'm not sure yet. But you're right, because I think we could easily walk ourselves into a dystopia where debugging Hello World involves 400 human beings, and that would not be good.
And then somebody will say, well, back in 2024, I listened to this podcast with Brian and Matt, and they told me I need to put everything in a component, and look at the mess that we have now. Yes, we don't want to. People, if you listen to this all the way to the end, then there's still ways to figure out best practices and
and this is the trick of software engineering, right? Is the engineering part of it is often learned through some hardships and some false starts, and that's the part that we're going to hit pretty soon here is when is the right time to use this technology this way, or when should we use it that way, right? When should we default to just using a library as a library compiled inside of a binary?
I think that problem gives me some hope, because a lot of times we see people choose technologies without any thought or consideration to observability or security, right? I mean, we've seen some people go full serverless just because they thought it'd be cool to run full serverless. Nothing to do about taking advantage of what, the pros and cons of serverless. And the reason why I say this gives me hope is that I think one of the things you'd have to do hand in hand to figure out how far, how low can you go to re-say how Andy said how small you can go. We'll go a little limbo there. Is with proper observability and understanding those different architectural regressions as you're planning it out. Like, okay, if we're at 10 versus 100, do we have any performance trade-offs? Do we get anything better? And by observing that as you go, taking and making observability and performance a first-class citizen as you're moving to WebAssemblies, I think that would help. We've seen that even in microservices, right? When you can start going into nano services and all this kind of stuff. But the key there is to observe it. and find out what that's going to be. And then obviously best practices will come from it. But even still, you would need to have that visibility to make sure you're doing the right thing. And I do have to give you a big kudos for saying dastardly. I immediately thought of Dirk Dastardly and Muttley and all those old cartoons. And I was like, you are the first podcast guest to say the word dastardly. So yeah. And Andy,
I will wear, I want a t-shirt now that says that.
I guess I didn't even pick it up. Yeah.
I don't know if this is like a Colorado thing, with kind of the like Wild West heritage that dastardly is just, it's just a word that's in the vocabulary, right? What else does a villain?
I haven't heard anybody say it in forever. I just know it from the old Hanna-Barbera cartoons. Like you're one of the first people I've heard in real life that wasn't like in some weird movie. Like, oh, we're gonna get that dastardly guy. It's so it's a bit old timey, but great. Andy, was there another question you had? I think
yeah. It's just the last thing because we need to get this unfortunately to a close soon. Matt, you talked about Fermion, actually not too much because you kept it really focused on the topic at hand, but maybe just like a kind of a final sentence or a final comment on what you guys are bringing to the table in that community.
Yeah, and what got us going was this interest in serverless, and so we built kind of two halves of this: a developer tool for building serverless functions into WebAssembly objects that can be deployed, and that's called Spin. Developer.fermion.com is where you can kind of find more out about Spin, all open source, all written in Rust, and then it supports a wide variety of languages, including Go and JavaScript, TypeScript, Python, Rust, of course. And then we have a Kubernetes runtime called SpinCube. We built this together with SUSE, Microsoft, Liquid Reply, and others. And this turns your Kubernetes cluster into a WebAssembly runtime side by side with containers. You can, for those of you who do a lot of Kubernetes work, how deeply is this integrated? It's integrated all the way down to the containerd layer, so you can literally deploy one Kubernetes pod that's a mixture of WebAssembly and container, images inside of it, and it can execute them side by side. So basically, we slotted in the WebAssembly runtime side by side with the container runtime, and you can use them both. It's really cool. So that's Spin and SpinCube are the two main things that Fermion is working on.
Perfect. And we'll add all the links, folks, if you're listening in, all the links in the description. Matt, thank you so much for doing this. I think I learned quite a bit about WebAssembly. Thank you so much for enlightening us. Brian, I hope you feel the same.
Yeah, I mean, as you can tell, I was absolutely silent in this one because it was just all learning. I couldn't even think of smart comments to make during it. Absolutely enlightening. I think there's a lot of
really
cool
nice
stuff.
way of saying, Matt, you talk too much.
No. Even anytime I even had a half of a thought, Andy was like right on it because he was so enthusiastic too, and I was just going to say something stupid anyway. But it's not that you even talk too much. This is all new, and I feel like we're seeing something right on the cusp. Like the idea of this being used on the back end is it's really exciting, and can't wait to see how that pans out. And now, I mean, I use Office 365 Web quite a lot, and now I'm going to know that's Wasm.
Yep.
That's so.
It's not only awesome; it's Wasm.
Yeah. Thanks for stealing my joke and repackaging it, Andy. Jeez. I guess we'll see mine fell flat, so thank you, Andy. Anyway. Yeah, I guess we'll wrap it up here then. Thank you again for being on, Matt. This was just absolutely incredible, and I hope this all goes very well. It sounds like there's a lot of exciting potential, and I can't wait to see what comes on. Thank you as well.
Thank you both for having me. This was great.
Awesome.
Thank you.
Been great.
Looking forward to seeing you at KubeCon in Salt Lake, I would assume.
That's right.
Yeah. Perfect.
All right. Thank you, everybody.
Thank you.
Bye.
Cheers. Bye.
Thanks.